think everybody can see that, and can you hear me all?
Yes, we can.
So I should thank you very much for the invitation to speak. It's always one of the good things to come out of COVID was this ability to give talks around the world in a way that would have been prohibitive. Although being in present is always more enjoyable, I have to say. But this is something wouldn't have otherwise have happened. And please, if you have questions during the talk, interrupt me, because either I understand someone will be monitoring the chat if I don't see it, but also just interject if you'd like, because particularly online, it's hard to, if you lose the thread, it's easy to lose the whole thread, and then it'll be hard for me to tell from here. So you may know that when the invitation included a topic, this is the talk I'm going to give here now is one that I gave to the Atlas collaboration meeting in Vancouver a couple of weeks ago, and that was actually a very enticing invitation, also because the mandate was to be opinionated and say where you think the most promising directions are, and I'm happy to be opinionated, and I think and I do think that there's some very underappreciated, but starting to be better appreciated, but very promising directions. And they all bear on the subject of naturalness and where we go from here, particularly given that the LHC found the Higgs, which is wonderful, but it didn't give us more direct clues about what new physics might be. So let me just advance my slides. There we go. So what I'll be describing is work done with these people. Most of it, the yoga models, when I get to them, were done with Danielle Deneen, who's a graduate student now, was an undergraduate at the time, and Fernando Quevedo and Philippe Brax. And the model is really, as you'll see, implementing exploiting symmetries that are generic to string vacua, it turns out. And they've been long recognized to be there. The first they were discussed was in the mid-'80s, but I think that they have, of the various symmetry consequences of string vacua, they're very underutilized. And that'll be the main message of these models. So I want to start off with the motivation for the where I'm going to go is that there are there's information for low energy physics coming from what we understand about high energy physics, which is kind of unusual in itself. And so to set up that, I would like to talk about why decoupling doesn't normally would make that a difficult connection to make. If you go normally, it doesn't matter what's going on at high energies. Whatever's going on tends to decouple from what's going on at low energies, and kind of that's why science progresses. But there are exceptions, and I'd like to focus on the exceptions. And tied up with those exceptions are issues of naturalness, many of which have they've been around for a long time, although there's many things that are called naturalness. But they've been suspect since the LHC. There's many things that were sold to us on the grounds of naturalness, technical naturalness in particular, didn't materialize. And so I'd like to start off with a kind of a critical assessment of that whole line of thinking and how it positions us now as we think about what new physics might be. And then I'd like to switch over to, so I will make the case that there are some things to which low energy physics can be sensitive, coming from higher energies. And I want to make a distinction between, I'm not the only person to be telling you that, the whole swampland program is saying the same thing. But I'd like to make a distinction between the swampland program and the program I'd like to describe, where the main distinction will be about as you'll see when I get to it, it's about the robustness of the predictions. I would like to argue that the ultraviolet physics can affect low energy physics in a very traditional effective field theory way, where it's robust symmetries are giving the power of the prediction at low energies, and so don't depend on all of the details, but do depend on the symmetries, as opposed to what I would say, the way I'd phrase the swampland program is the proposal there is that ultraviolet physics or low energy physics is UV sensitive in a much more specific and dangerous way from the point of view of understanding the robustness of our understanding of physics at low energies. And so that contrast, I hope, will become clear as I go through the second part of the talk. Okay, so let me set up that story, the naturalness story, and you know, we're all in the same business, so we know the standard model works so well, but it doesn't work perfectly. And so what do we do? And I want to argue here in this first section that many of the problems are to do with gravity. So let's start with what we agree on, what we're correcting. So the standard model itself, as opposed to the standard model effective theory, say, is the renormalizable gauge theory with the the normal particle content and the normal gauge symmetries. And we know that it's incredibly successful quantitatively within its domain. Now, we believe that we're not satisfied anyway. And I want to go through the list of the reasons that we're not satisfied. And that list often contains many things that are aesthetic, like counting up parameters. And I will not count any of those because I have no insight as to what nature finds beautiful. But I want to focus on experimental problems that the standard model is not dealing with. And so the first one traditionally that we ran into was neutrino oscillations. That the standard model, the renormalizable model, would predict they don't happen, and they do. And so that's a problem. The second thing is, the standard model doesn't include gravity, and certainly gravity exists, and it's not renormalizable. So it's not just so simple as saying, well, we'll just add another piece to the standard model. There's all the evidence for dark matter and dark energy, which I'm sure you're familiar with, and those are not included in the standard model. The dark energy side of it, there's a distinction. Dark energy could very well be, as far as the observations are concerned, just the vacuum energy associated with standard model fields. The problem is with the size of the vacuum energy that's measured, and that's where some of the naturalness issues will come in that I'll clarify. And the final one I would list on this list is a little bit different in character because it's not such a direct experimental conflict, but there's a class of initial conditions. We have a very good picture of cosmology, provided that we start things off with exactly the right initial conditions. And the two main ones that people mostly focus on are the primordial fluctuations, the correlations in the sky that are coming from things that were happening, and they have to be put in a scale invariant, close to scale invariant pattern of fluctuations has to be put in by hand. That's something which is, you could just take that as an initial condition, but if you want some sort of a dynamical explanation, the standard model doesn't give it to you. And similar story applies to baryon asymmetry. You could just choose to stick it in, say baryon number is conserved, and we started off with a small amount. But if you want something more dynamical, then you need something else. So the way we approach those problems, typically, if you think in terms of energy, so here's an energy goes up, and the lines are states, and the problem in the orange dotted line is the cutoff above which we have not been able to probe. Standard model are the blue things, and we add new things. And so if you think about neutrinos, the simplest thing to add is sterile neutrinos, other things that are light that could be seen in experiments. We couple them weakly enough to the standard model that they wouldn't have been seen before, except for the places we're trying to use them to describe what we see. And of course, the neutrino example also illustrates that we could have introduced new degrees of freedom that were heavy, and they, and most famously through seesaw models, and those alter the effects of ordinary particles at low energies. And that's usually most efficiently described by integrating out whatever that heavy physics was and just directly talking about what the effective theory is at low energies. In this case, the integrating out of heavy sterile neutrinos would have given us a dimension 5 term involving standard model fields, which has the consequence of giving us a neutrino mass. And the coefficient in this effective operator involving 2 lepton fields and 2 Higgses involves the microscopic couplings and goes inversely with the mass. And that's kind of the origin of the decoupling story, that the bigger the mass was, the smaller that interaction is. And that's kind of the beauty of the seesaw mechanism. And more generally, that's typically true, that all the dimension 5 and higher operators are suppressed by whatever the mass is that we integrate out if it's a heavy mass. Now, if you think about how we handle gravity in the same way, we have to add a new particle, the graviton, that's the dotted line at the bottom. But the theory that describes its interactions is already non-renormalizable. So that means it's making reference to some scale, which typically is parameterized in terms of Planck scale. And what's unusual now, as opposed to what's nice about being alive now, as opposed to when I was a student, is that there exist UV completions which describe gravity in a way, in a sense that you have effectively renormalizable, better than that, finite interactions amongst heavy degrees of freedom, which have the property that when you integrate out the heavy degrees of freedom, they can describe Newton's laws and Einstein's relativity at low energies. So unusually in history, we have a picture of what could be going on in the UV. And the theme of the talk is, is there information in that we can actually use at low energies besides the existence of gravity and its successful description of where Einstein's equations come from? Just continuing the story of the dark matter, we had light things that are coupled again weakly, possibly gravitationally to ordinary matter. Baryogenesis and the initial condition story, it's the same thing, typically heavy stuff, but in this case, it's heavy and you don't integrate it out because you're imagining that in the inner universe, you were at high enough energies that you actually were at those energies and they were relevant. So, but it's all a very similar story. And for dark energy, the only one thing I would say about that is that there's really no paradigm that everybody agrees can work. But the one thing we do know is that if the problem with dark energy is understanding its size in a natural way, then what we do know is that whatever solves it, it won't be a UV story. It'll have to be an infrared story, because the small size of the dark energy is so small that integrating out the electron gives too large a contribution by 36 orders of magnitude. So whatever the physics is that's changing things, it has to already be intervening at the electron scale. So in essence, the dark energy naturalness problem will turn out, when I get to it, to be not a new physics problem at high energies. It's really a standard model physics problem at low energies. And so whatever it is that fixes things, it'll have to have a component at low energies, which is encouraging, because if there were to exist a satisfactory theory that suppresses the dark energy in the way that we think it should be suppressed, it's almost certainly going to have other consequences, because it will involve light degrees of freedom that are coupling to things like the electron, which we can measure very well. That's the prize that you aim at when you think about dark energy. Now, the main point for this talk is everything there except for neutrinos involve gravity in the framing of the problem. Besides the existence, but the evidence for these other things is coming generally from cosmology, and which is all about seeing things through their gravitational interactions. So then that leads to the question: so can we, since we do have a candidate, there are many candidates for what the UV completion of gravity could be, but I'm always going to mean by that string theory, not because I'm a diehard string theorist, but just because string theory has developed to the place where you can actually ask these questions very concretely in a way that the other frameworks I don't think have been developed yet, but they possibly can be. And when they are, these are the questions you'd ask. But string theory is already insight. It provides insight because it gives a very concrete, then it's been explored enough that you can see a wide variety of the implications it could have had at low energies. So normally the answer to would be, you'll never see any implications for high energy physics at low energies, because decoupling, this fact that effective interactions go like 1 over the masses, is always what you're fighting. But here I want to emphasize that there are specific exceptions to that statement, that heavy physics decouples from light physics. In particular, if you think about it, the way that you normally think about decoupling is the poster child of decoupling is atomic physics and nuclear physics. We didn't need to understand nuclei before understanding atoms in a detailed way. But it's not quite true. You had to know nothing about nuclei. You did need to know its mass and its charge, and depending on how accurate you want to be, you might need to know its lowest electromagnetic moments. And so the proper statement is that there are specific things that can be sensitive to small distance physics, although most things are generically insensitive to small distance physics. So the utility is in identifying what those things are that are sensitive to high energy physics. And the opportunity here is that properties of the scalar potential in particular, and how that gravitates, are among those things that are UV sensitive. And cosmology, success in describing cosmology tends to depend strongly on what the properties of those things like scalar potentials are. Small vacuum energies and very light scalar masses are the things that are often used in cosmological constructions. And those are the kinds of things that like to be UV sensitive. So there's an opportunity to learn something about high energy physics at low energies. And I want to argue that the opportunity is probably is more when you follow it through in detail than just that naive statement would have implied. So that leads us to what exactly is it in low energies, at low energies, what is the UV sensitive part at low energies? And so the picture here is showing you that the nature could have many scales, and I've started at the bottom with the weak scale, and we go up to the Planck scale there, and I've put up some tick marks where you might, in your favorite theory, have some scales. And normally what we do is we integrate the heavy physics out to look at low energies, as I've been saying. And what's nice about that effective field theory way of thinking about things is it makes the distinction between what's robust and what's UV sensitive. And so if you think about quantum chromodynamics as the example, an example of a UV insensitive statement about the low energy limit of quantum chromodynamics are the soft pion theorems. We know that pions behave as do the Goldstone bosons of SU2 cross SU2 goes to SU2, that symmetry breaking pattern. And all that goes into the structure of their interactions at low energies is that symmetry breaking pattern. So all that QCD is putting into the prediction is that that pattern is what's going on in the ground state of QCD. And beyond that, the symmetries drive you all the rest of the way to describing what the low energy pion properties are. That's an example of a robust prediction. And that's kind of the generic effective field theory kind of prediction. But an example of a UV sensitive prediction would be, say, the value of a proton, the proton mass. That's something which is not a symmetry consequence. It's something that QCD will predict for you when you calculate it properly, and other theories which might agree on the pion properties if they had the same symmetry breaking pattern could disagree on the proton mass. And if so, then that measurement of the proton mass is discriminatory about what's going on at high energies. Now, naturalness, the way I'm going to talk about it, not the aesthetic naturalness, I don't like small numbers, but the technical naturalness, which I'll define in a second, is a special case of this UV sensitivity. And it's the special case where the UV sensitive parameter is expected to be large, and it's found not to be large. So I'd like to take you through that in a way which I think many of you have seen before, but I just want to make sure we're all on the same page. So the main observation is that we have some effective interaction, and we integrate out some physics with some mass scale m. And what we know is that we get, as I've said before, the effective interactions come in with powers of the mass set by the dimension of the interaction. So in the dimension 5 neutrino interaction, we had a 1 power of inverse mass, but other interactions could have different powers. Photon-photon scattering would have had 4 powers of the mass. And the main observation is that different particles that could appear in that loop, they have different masses, you add them together, and as long as the mass is in the denominator, it's the lightest mass that wins. So if you look at photon-photon scattering, it's the electron in the loop that you care the most about because it's the electron mass that's the smallest in the problem. Now, that's kind of generically true. It's not always true. In the weak interactions, we don't look for weak interactions mediated by inverse electron masses. And that's because it has to be consistent with the symmetries of the problem. And so, for example, in radioactive decays, you needed a W boson to break the symmetries in the standard model. And so the flavor symmetries that would have forbidden the decays. And so there has to be an inverse W mass in your amplitude somewhere. But all of the powers of mass don't have to be W masses. And so there are nice examples in neutrino physics where there are processes such as neutrinos scattering and emitting 3 photons, where there's a minimal suppression by the W mass, but then all the rest of the dimensions are coming from the electron mass. And it's typically true the lightest mass that can appear is the one that wins. But the exceptions are when that power is negative and you're sensitive to the positive powers of the mass, because then it's the largest mass that wins. And those are the ones that are the traditional couplings that you worry about in naturalist arguments. And so in particular for the standard model, there are 2 dimensionful parameters, the Higgs mass and the vacuum energy, sigma, in this the way I'm writing it. And the main message about naturalness is a small value for positive dimension coupling is something for which there's no symmetry that can make it small, because we always have to ask, it's the dominant mass that is consistent with the symmetries that's important. What's important about these interactions is that there's no symmetries, or there's very few symmetries that forbid them. And so the biggest mass in the problem should be the one that's dominating. And if you find evidence that it's not dominating, that's when you're learning something about the UV. And so that leads to the precise statement of technical naturalness. You have all these scales in nature. When you write a Lagrangian down, we used to think about it as being, that's God's Lagrangian, but really now we just think it's just some bookmark. It's an effective theory which could be applied at any scale. So you could have integrated any of these things, and we could be talking about the the effective theory at any energy scale. And when you compare the parameters in various effective theories, for example, supposing I integrate out this particle whose mass is 10 to 11 GeV, and supposing it contributes to the Higgs mass, then if I look at the parameter in the action, which is describing the Higgs mass at the TV scale, that's what I'm calling M here. The physical prediction for the physical mass, which is a measured number, is that parameter plus loop corrections in that bottom line here. But in the effective theory above the mass of this particle of the 10 to 11 GeV, there's a different prediction, and that's the Higgs parameter in that theory plus the loops of that heavy particle plus the standard model loops is what would be in the physical mass. And those first two things both appear as the contributions in the low energy theory to the parameter, the Higgs parameter, because the loops of the heavy particles aren't around to be done in the low energy theory. And so what's happening with this way of expressing the electroweak hierarchy problem would say, we measure the Higgs mass to be 125 GeV. So in the effective theory at the TV scale, that parameter M in our standard model Lagrangian is also of order 100 GeV. But in the effective theory above this scale of 10 to 11 GeV, the number M tilde is actually an enormous number, and it cancels to something like 11 decimal places between with the loop to give you a small number in the effective theory. And that's something which is very unusual. Normally what happens when you have a hierarchy of scales we have many hierarchies of scales in nature, not just in particle physics, but in all kinds of, in all areas of physics. And what normally happens when you have a hierarchy of scales is that the smallness of the parameters involved can be understood in any effective theory you choose to ask the question in. So it should be true if you understand things in a technical naturalness is defined to be the situation where if you have a small ratio of parameters, you understand why it's small at the fundamental theory at the highest of energies, but you also understand why it stays small as you integrate out physics to get down to the energies where you do the measurement of what that parameter is. And if it's true that a parameter is small and it stays small, that's what it's meant to be technically natural. Sometimes what people mean by technical naturalness is they ask if there's a symmetry in the problem that is present in the when this parameter goes to zero. And that's a sufficient condition for the technical naturalness I'm talking about. But this is, I think, the general condition. This is the thing that you normally ask for. And the only reason, you could choose not to believe that this is a criterion that physics should satisfy, but you need to recognize that it's a radical position in the sense that all of the hierarchies in nature we understand, except one, satisfy this. And the one we don't understand is the cosmological constant. All the other ones, like the electroweak hierarchy, involve physics we don't understand yet. So we don't know yet if those are technically natural.
Yeah.
And so
may I ask a question? May I interrupt you? Just
Please.
To understand this point. So about technical naturalness, but okay, most of us are used to the situation when the smallness of parameter, technical smallness, is protected, is a consequence of symmetry, as you mentioned. But you say that this is a sufficient, but not necessary condition.
Yes, right.
Yeah, and what is any example of some other condition of naturalness, not related to symmetry?
Okay, I would call the symmetry one. I would call that Tuft naturalness, just to have another name. But an example in the 80s, there were examples of supersymmetric models which they were said to be supernatural in the sense that there was no symmetry reason why terms in the superpotential, for example, were small. But they were, once you made them small, the high energy theory, they stayed small because of non-renormalization theoresms, for example. And that would be an example. That's kind of the best counterexample to.
Yeah, but isn't this a consequence of supersymmetry, non-renormalization theorem? This is a symmetry.
It is, but the question then is how big is the breaking? And so in this, in the examples I have in mind, there's terms in a grand unified theory, for example, that you could have, supersymmetry is going to be broken at much lower energies, and the terms that are supernatural in this way, if you had asked, are they forbidden by supersymmetry? The answer is no, because you can actually write this parameter down. So if you turn the parameter off, you don't get more supersymmetry than you had before, and that's normally the criterion you would have asked for in Tuft naturalness.
Okay. Yeah. So more sophisticated. Yeah. influence of symmetry consequence. Okay.
But I think it's fair to say that tough symmetry, tough naturalness is for almost all cases the same thing, in the sense that when we say that we've got a technically natural thing, normally that's what we're using, the tough naturalness. So it's kind of a pedantic distinction, but I think it's a real one.
I see. Okay, thank you.
Yeah. So the I'm probably beating you over the head with something that you're happy with anyway. But the utility before the LHC started, I think, of this technical naturalness criterion was that the good thing about it is that if you're trying to make things technically natural and physics above the electroweak scale, you can't put that physics at the Planck scale. It has to be coming in at low energies in order to solve the naturalness problem. Because if it was happening at the Planck scale, you could integrate that physics out and then you have the problem back again. So whatever the degrees of freedom are that you're adding, the useful thing about the naturalness criterion was that they had to be there at low energies to fix your problem. And now you could ask, so should we be worried in the LHC that we haven't seen these three things? These are basically all the proposals for technical naturalness fall into these three categories, roughly speaking, and none of them were seen. And I would say that I'm not worried about those things specifically because there's kind of a fine line between whether they had to be there at a TeV or 100 TeV. And that's to do with whether or not you're, how unhappy are you to fine tune things to 1 part in 100 as opposed to 1 part to the 10 to the 15. I think there's a room for debate. There's a gray area as to what's acceptable at low energies. And so I think that there's really not a definitive repudiation of naturalness, technical naturalness in the electroweak hierarchy. I think the real problem for technical naturalness is the cosmological constant problem. Really the fact that there's a scale that's at the electron volt scale or sub-electron volt scale that the electron and every particle in the Standard Model wants to screw up, that's the real problem. And I think that if you kind of said if I wanted to not believe in technical naturalness, if I wanted to throw in my face the best evidence why that's a bad criterion, the cosmological constant is the one, because when we integrate out the electron, it gives us and there's no symmetry which forbids the electron from gravitating, giving a vacuum energy that gravitates at the level which is 10 to the 36 times too large, and it just gets worse the bigger you go. It's 10 to the 54 at the weak scale. I do not worry about the Planck scale, which is often what's phrased as being the problem of the cosmological constant, because supersymmetry could kick in at 1,000 TeV and solve it from then on up. But the real problem in the cosmological constant is the electron. And so that's something it's probably the particle you thought you understood the best, and it's at extremely low energies. And that's the one threat, I think, to this picture of naturalness. And so that's really what's going to be organizing I'm aiming at in the discussion that I'm heading down when we talk about what UV physics what can we extract from UV physics, keeping effective field theories as our guide. That's a natural place to stop for questions if there are any more questions, because I'm about to jump into the second half. And I've finished the motivations. Okay, so the second half is, what can we say usefully at low energies, given that we have a picture that gravity is coming from a theory that we have a concrete example of what that theory could be. And so it's what can the knowledge of the UV completion of gravity say to us at low energies that we can test is the question. And that should be hard, because it's, decoupling, we should be fighting decoupling. And so we're looking for the specific things at low energies which are UV sensitive. And before I tell you what I think, the way to think about that, the way I think you should think about that, I want to do a detour here to summarize the swampland program, which says the same words. They would like to argue that, and I think they honestly are trying to find what the low energy implications are from from the observation that string theory could be the UV completion of gravity. And I want to mostly highlight the difference between their point of view and what I think is a more fruitful point of view. So why should you think that there is something to learn? The first observation is that we have an example. And this is something which it's hard to overemphasize this. I grew up not having any examples of a UV completion of gravity, and so you could not ask these questions. But given string theory, there are some things which are very plausibly emerging as being generic predictions of string theory. And they kind of come with a hierarchy of reliability, I would say. And this list contains some of them, where the ones at the top, I think, are most reliable, and the ones at the bottom are least reliable, or less reliable, say. And so in particular, I should have said, so it seems to be true that in perturbative string vacua, you can pretty much prove that there are no global symmetries. Everything's a gauge symmetry. So that means that in principle, if you had an exact global symmetry, that sounds like something that should not be completable to something at high energies that includes string theory. And then there are other things that are also very generic, like there's a lot of supersymmetric solutions, although that tends to be more about having computational control over the approximations. It's more difficult to do that in a non-supersymmetric context. There's no example of a string vacuum which gives you just the standard model at low energies and nothing else. So if you are trying to find things that are rare, that's rare. That you can get the standard model, but typically with a whole bunch of other things. But the one that people focus on the most in the swampland program is the difficulty in getting de Sitter solutions or getting inflationary solutions. It's hard. It's a hard business in string theory, and I would say it's hard mostly because if you're trying to find a potential that you think is inflating, you're looking for some very shallow potential. But in order to compute that potential in string theory, you have to know what all the fields are and what the potential looks like as a function of all of them, not just the inflaton. Because you can imagine if you have a very shallow direction in one direction in field space, but if another direction is very steep, it doesn't matter how shallow the first direction is because you're going to go the steep direction. So you have to really know what all the directions are to find the shallowest direction to roll. And that's what makes it complicated because there's a lot of fields in the problem. But they've made a lot of headway on it, and it's not easy to do. And there's a debate happening in string theory now as to how reliable the calculations are that give you de Sitter-like solutions. So that's led to the swampland hypothesis. And I think the thing that they don't normally say, but which I would make explicit here, is the assertion is that for a swampland person, de Sitter solutions are UV informative in the same way that the proton mass is UV informative for QCD. So if you know that it's zero or you know it has a particular value, that's telling you something directly about the ultraviolet theory in a way that is not just a symmetry consequence. That's the assertion. And so because of that, then if you buy that assertion, then that would mean that there are many effective field theories out there which have no UV completions, and we should not be thinking about them as candidates to describe nature. And so there's a process in which people are trying to categorize the things that can't be completed to UV completion, including gravity. That's called the swampland, to contrast it from the landscape of solutions that you get in the low energy limit of string theory. And so for them, it's a priority to identify who's in the swampland and who's not, because the belief is that things that we see, like near de Sitter histories or dark energy now, are hard to get in string theory. And so that means that there should be a tension between what we see and what we can get from high energies. Now, I think the evidence for this is marginal, and I think there's very good evidence that some things that are held up as being consequences of the high energies are true. Global symmetries not being present is pretty much a theorem in string theory, and so the absence of ultra weak forces that are weaker than gravity is also seems to be it's not a theorem, but it's something which is very plausible. And then there's a hierarchy of less and less certain things, which culminate with the de Sitter vacua, and there's an ongoing debate now in string theory about whether de Sitter vacua are present or not. Now, but I think it's true, it's fair to say that there's what I would call swamplementarity going on. That the more certain you are that there's a statement you can make that's an exact consequence of the UV theory, like there's no global symmetries, the less informative it is at low energies. So there's nothing, the absence of global symmetries doesn't mean that you can't have an effective theory where you stop at some fixed order in the expansion. So you keep only at dimension 6 or less terms where it looks like there's a global symmetry. If it were true that you can't get global symmetries to any order in the energy expansion, then that would rule out the standard model because the standard model has accidental global symmetries. So you can get lots of accidental global symmetries in an effective theory. And the problem is that in an effective theory, you never see more than the lowest energy interactions. And so it's difficult to know how to use this information that you can't have global symmetries, for example. What people like about the de Sitter proposal is that it can be very predictive, but it's also not clearly a consequence of high energy of string theory. And so that the more predictive your consequence is in this program, the more difficult it is to be sure that it came from string theory and it's not just a conjecture. So there's a lot of conjecture physics that happens because of that basic tension between the robustness of the predictions and the robustness of the conclusions coming from the UV physics, which is a special case of decoupling, I think. So what's a better way to approach things, I think, is to do things the traditional way, to ask instead of asking the proton mass question from gravity, ask the soft pion theorem question for gravity. What are the symmetries of the problem? And are there any symmetries in the problem that would make these rare things like de Sitter space understandable? And I would like to argue for you that there's two symmetries in particular, and they in particular go a long ways towards explaining the difficulty in finding de Sitter vacua. And once you recognize the role the symmetries play, it helps in making better constructions of getting de Sitter vacua. And I want to argue also that these symmetries, because they constrain the shape of the scalar potential and how it gravitates, are relevant to dark energy, and they suggest a direction in which we could be exploring, which is probably fruitful from the point of view of exploring the low energy consequences of string theory, or your favorite UV completion. I'm calling this scaling the landscape because one of the symmetries, one of the very generic accidental symmetries is a scaling symmetry. That's kind of the origin of the scaling story. So we want to do the chiral perturbation theory story. We want to ask, are there symmetries at low energies that are accidental, possibly not exact, that can constrain how we think about what's going on? And the two symmetries I want to focus on are scaling symmetries, but I'll first talk about supersymmetry. I think supersymmetry, the point will be that supersymmetry and scale invariance together is actually much more powerful than either of them are separately. But for supersymmetry, you might already have a problem that supersymmetry, we haven't seen it. And so we already know that the particle physics sector in the world is not supersymmetric to within the approximations that we can measure. And so I want to emphasize here that the supersymmetry that I'm talking about is not supersymmetry in general. It's a supersymmetry of the gravitational part of your theory, because these problems that we're trying to address are driven by gravitational response of things. That's the part that's important. That can be much more supersymmetric than the particle physics sector that we explore in colliders. So what are these symmetries and why are they? I want to now argue what these symmetries are and why they're generic in string vacua. And then I will go and look at their implications, or an example of what their implications could be. All right, so first supersymmetry. So how can you have supersymmetry in the gravity sector? Why should that be something you would expect at low energies, given that we have no evidence for supersymmetry in colliders? So that in all of these theories, the string theory is no different from any other supersymmetric theory. If you have if you spontaneously break supersymmetry, you have supermultiplets, and they split, and the bosons and the fermions split in mass. And what's typically true is the size of the splitting of any one supermultiplet is controlled by some expectation value. I'm calling it F here, that breaks supersymmetry. But it's also controlled by the strength with which the multiplet you're interested in couples to the field whose expectation value breaks supersymmetry.
Just a question.
Yeah, go ahead.
And this supersymmetry is a global symmetry.
No, I'm thinking supergravity, but for the purposes
of supergravity, because global symmetry is not supported by superstrings, right? As you said, or no higher theorems. Yeah.
Not as an exact symmetry, no. But there will be. I'm going to be talking about supergravity, but it's true that there's a limit which when gravity is weak, where I can think of this as being an accidental global supersymmetry if I want to, but I don't need that in what I'm going to say now.
Mm-hmm. Okay, thanks.
So the statement will be that that a multiplet, so there's some field gets an expectation value that breaks supersymmetry, and then the multiplets in your theory get masses which are proportional to the strength with which they couple to that expectation value. And so you typically get a formula like this one, where the splitting between bosons and fermions is some coupling times some expectation value. And so that means that the weaker your couplings to things, the smaller your splitting will be. And so it's not at all unusual to find that gravity is the weakest split, or the split by the least, because gravity tends to be the weakest coupled sector in your theory. It's got the weakest interactions in your problem, in particular to this whatever it is that breaks supersymmetry. So having a hierarchy between the standard model sector and splitting between those particles and their superpartners, having that be a much bigger scale than the splitting between the graviton and the gravitino is not at all unusual in a string vacuum. But now supposing that your UV scale that you can measure up to is here, then what you'd expect to see at low energies is basically a supergravity. You'd have the gravity sector comes with superpartners in your low energy world, but your particle physics sector doesn't. And so if you wanted to think about that in the terms of accidental global supersymmetry, what that would mean is if I do a supersymmetry transformation of an electron, I don't get a selectron. I get an electron plus a Goldstone fermion, but that Goldstone fermion then mixes with the graviton and gives it a mass. And so the rules for how you associate superpartners to the particles that you see in this low energy theory are different than the ones that you're used to if you're used to thinking about linearly realized supersymmetry. And what's nice in the last 10 years is that what you're led to in this kind of a picture is your low energy world should be supergravity, but coupled to non-supersymmetric matter, which sounds kind of paradoxical, but that's now a solved problem. We now know how to understand how to couple non-supersymmetric matter to supergravity in a consistent way. And essentially what you do is you take non-supersymmetric matter, you can make it for free globally supersymmetric by coupling it to a Goldstone fermion. And then it's an example of a globally supersymmetric theory, which you can then gauge and couple supergravity to. And so what happens is that you end up with a systematic way of constructing the low energy limit in this very plausible world that you could have gotten in a fundamental theory where gravity is the weakest force and supersymmetry is broken. So that's the motivation behind thinking that the gravity sector is supersymmetric. The particle physics sector is not, but how they couple to each other is an understood thing. Now, the scaling symmetries I want to talk about have this specific form. The metric will scale by a constant. I'm calling it lambda. Your other fields in your problem will scale by some other power of that same constant, possibly a zero power. And then when you do that, your Lagrangian scales by another power of that same constant. So it's not a traditional symmetry in the sense that the action's invariant, but it is a symmetry of the classical equations of motion. And so it's something which is often has consequences for, say, compactifications, if you're trying to think of solutions to the classical equations of motion. So I claim that this kind of a symmetry is at least one, often more than one, symmetry of this type is present in every single string vacuum that has ever been given to you. And here's why. It's a very simple argument. In string theory, there are no parameters, it's just fields. And so when you do things like weak coupling expansions or low energy expansions, you're really expanding in powers of some field. So your Lagrangian comes to you in a series of multinomials in these fields, phi to the m, psi to the n. And so now it's kind of a trivial statement that if I take those fields and I scale them, any one term in that series will scale in a specific way. In particular, the leading term will. And so that's the origin of these symmetries. They're always there. And so you can go through the exercise as we did in several years ago of taking all the various string vacua, and you can find all that. You can just explicitly see, it's nice to have a general argument, but it's also good to see the symmetries are explicitly there in the vacua they have. In 11 dimensions, that's believed to be a strongly coupled vacuum. So the only expansion you do is the low energy expansion, and there's only one scaling symmetry in the 11-dimensional supergravity action, it turns out. But in 10 dimensions, those are weakly coupled string vacua. You do the low energy approximation and you do the string weak coupling expansion. And it turns out there's a 2-parameter family of scaling symmetries we've shown here, where U and W are 2 numbers. You can take U to be 0 and W to be 1. That's one of the scaling symmetries. And you can take U to be 0 and U to be 1 and W to be 0. That's the other one. And you can go through all the different string vacua, and these symmetries are just generically there. Now, the reason that you care is that those symmetries, scaling symmetries in particular, are very, very constraining if you're looking for de Sitter solutions. And that's because of the following argument. The potential that you get from this kind of a symmetry has the form shown. And if you differentiate that a couple of times, you get these 2 identities that are in the boxes here. And the bottom one just says something which you probably believed anyway. It says that if you find a place in field space where the fields all vanish, so that's the scale invariant point, where it doesn't matter if you scale things by a constant, that will be a stationary point to the potential if it was a potential of this class. The top one is the more interesting one, because it says that if you have any minimum at all, but in particular, it does not have to be a scale invariant minimum. So if we have scale invariance, we're going to want to spontaneously break it because we know that there are masses in our problem. We know that the world around us has scales in it. But if you find a solution that breaks scale invariance spontaneously, the potential has to be 0 there. So unlike what's the usual situation with naturalness is that if you have a symmetry and you break it, you lose the protection that the symmetry provided. But in this case, you don't. If you spontaneously break scale invariance in this particular sense, the potential had to be 0 at the scale invariant point, but it has to stay 0 if you spontaneously break scale invariance. And the reason for that is simple. If you imagine you give me a non-scale invariant solution, anything I get by a scale transformation from it is another solution. In particular, if I scale it to 0, that is the scale invariant solution. So the scale invariant solution is one of the various solutions that are related by scale transformations. They all have to have the same energy because they're all related by a symmetry. And it has to be 0 because one of them is scale invariant. That's very much unlike the Mexican hat potential, where you've got a line of broken solutions at the bottom of the hat, but then you have a maximum, which is a symmetric point, and they're disjoint from one another. You can't get from the maximum to the minimum through a set of solutions. Scale invariance is different because the invariant solution is on the same manifold as the broken ones. And so you continue to have the protection of the breaking of the scale invariance, even if you spontaneously break it. So that was something that people realized in the late 80s. And immediately after they did, Weinberg shot it down with a no-go theorem. And his no-go theorem basically said, that's all wonderful. Supposing you had an exactly scale invariant theory, radiative corrections, even if they're scale invariant, can't stop you lifting the flat direction. And the question in these theories, if you're trying to solve the cosmological constant problem with scale invariance, is why did scale invariance spontaneously break? It will always be true that the potential is zero at the minimum, but it's not clear why corrections will allow you to break scale invariance and have other scales be non-zero, even though the potential is zero. And of course, the cosmological constant problem, the problem is that you have scales that are not zero, that are different from the one that you see in the potential. So, but that tells you that if to the extent that that symmetry is playing a role, you're going to have a hard time finding de Sitter space. And so if you look at the way people find de Sitter space in string theory, and I can kind of see that I'm coming up on my time here, I'm closer to the end than you might think. The way that people break, they have to stabilize all the various other fields in the problem, and they do it in a way where they choose the superpotential in their theory to stabilize the other fields. And that implicitly breaks these symmetries hierarchically in a way that it breaks the scale invariance more than it breaks the supersymmetry. So you end up perturbing around solutions that are anti-de Sitter space, because anti-de Sitter space is the one, that's the supersymmetric. You can't have supersymmetric de Sitter space because de Sitter space breaks supersymmetry. And so because they're perturbing around anti-de Sitter solutions, it's of course hard to be infinite, have small corrections get you all the way up to positive values of the cosmological constant if you start with negative values. But that just suggests that what you need to do is find a way to make the hierarchy of symmetry breaking different, because the scale invariance is going to love to have you near flat space. And if you perturb near flat space, you can go up and down equally easily. And so de Sitter space should be no harder to get than anti-de Sitter space. And that's essentially what happens. If you stabilize things using the Kähler potential rather than the superpotential, then it's actually much easier to find de Sitter solutions. And I'm not claiming that these are string solutions, but once you see how it works in the supergravity at low energies, then the question is, can you lift that to a string completion? And I suspect that will be liftable, but I think that's an open question right now. But I think the organizing your thinking in terms of these symmetries is super important for that. And more importantly, there's a mechanism here for suppressing the size of the scalar potential, because what happens is that supersymmetry with scale invariance is more powerful than they each were separately. And what happens is everyone knows that if you have only an approximate scale invariance, that will even if you had arranged the potential to be nice and flat at the leading order, the corrections will lift that flatness. But what supersymmetry does is it makes the lifting smaller than you would have bargained for. Because if you expand in some small parameter, supersymmetry can make the first correction also not lift your flat direction, and it can postpone the lifting to subdominant order in whatever your expansion is. And that's a mechanism that hasn't been exploited in trying to understand the smallness of the vacuum energy. And so the final few slides will be, I'm going to give you the first steps towards what a model would look like that exploits that to try and understand why the vacuum energy is small, and it will have robust predictions. And the models that you're led to in this way are called yoga models because they have a natural relaxation in them, as the name, that's where the name comes from. And the expansion that I'm going to be talking about will be, I'm going to imagine there's a field which has got a very large VEV, which will be the scale invariance field, the dilaton field. And because it's large, we'll be expanding the action in inverse powers of it. And because the field is so large, a suppression by one order of expansion will be a supremely big suppression. And that'll be how we're going to try and get a small vacuum energy out of the problem. So here's how it works. So, and when I describe, was there a question there? Oh, okay. So I'm describing, what I'm not going to describe is there's a whole inflationary story here, which is actually a very good story, which if anyone asks, I can tell you. But the best models of inflation from the point of view of the data are Goldstone bosons, not for internal symmetries, but for scale invariances, it turns out. And that's probably very suggestive right there that scale invariance is playing an important role. But what you're led to, if you try to use this mechanism to understand this, standard model physics, is the minimal ingredients are you have a Goldstone boson, a dilaton for the scale invariance. There's a field that transforms under the scale transformation, and the leading term of the Lagrangian should be scale invariant in the way I described, that it scales by some factor. There'll be corrections which will scale differently because they will depend on different powers of these fields. And so that leads you, I'm going to call that field tau. Now I'm going to imagine that, where does supersymmetry come in? I'm going to imagine that that this field tau is in the gravity sector. So it's more supersymmetric than the standard model is. So it comes with superpartners, and in particular, that means that it has to have a scalar superpartner, which is typically in string theory, it's some axion. So I'm going to imagine that I've got an axion A and this dilaton tau. And then if I make the Lagrangian scale invariant, it turns out the leading term will be this. I've got the Einstein term there. I've got a kinetic energy term. If I scale tau and A by a constant, and I scale the metric by a constant, then things are invariant there. I'll have to tell you what the potential is in a second. But the important thing is that since this is the kinetic energy is it's a supersymmetric part of the theory, I've told you in secret here what the Kähler potential is for the theory. And everything I'm going to tell you from now on is just going to be take the Kähler potential for this theory, think of it as a series in 1 over tau, and just turn the crank and get what you get. But there's some general things that happen, and I'm just going to mostly focus on the generality of it. But there's no magic in what I'm going to describe here. And in particular, in a supersymmetric theory, when you find the action and you write it in this way, which is in the Einstein frame, where the coefficient of the Einstein term is just the Planck mass, you have to do a rescaling of the metric. So the way that the standard model will couple to these fields will be through a rescaled metric. And that's going to be important in the low energy description of what the implications of these fields are. And it turns out that the scaling that you have to do is given in terms of this Kähler function K, it's not something you get to choose, it's just dictated to you. And it turns out in this particular example, I'm showing you to be G goes to G over tau, or this tau. Now, the reason I tell you that is when I couple the standard model now is a scale invariant thing by construction, and it couples to tau through the metric. And that means that tau will appear everywhere you had dimensionful parameters in your theory. And in the standard model, that's only the Higgs value. So the parameter mu is the only thing that will see this scale, and it'll go like some particular power of tau, and everything that depends on mass, every mass scale will depend on tau in the same way, except for one. So in particular, the standard model particles, except for the neutrino, which are linear in the Higgs mass, will scale like 1 over the square root of tau, it turns out, if that's the way the metric scales. Sorry?
No, please continue.
Yeah. Okay. So the exception is the neutrinos, because the neutrinos, as we saw, they get their mass. If they get their mass from a dimension 5 term, it's quadratic in the Higgs mass, the Higgs valve, and so it would see 2 powers of this scale breaking. And so you're led to a generic world where all the standard model scales are set by 1 over the square root of tau, and neutrinos are 1 over tau, and that actually numerically would work if tau was 10 to the 18th. It turns out. And if your basic scale in the problem was the Planck scale. So that's going to be the way we're going to work things. We're going to imagine tau is that big. We're going to be expanding in powers of 1 over tau, really good approximation because tau is huge. And understanding why the value of tau is going to be telling you why the electroweak hierarchy is what it is. And it's also going to tell you why neutrino masses are what they are. And ultimately, it'll be telling you why dark energy density is what it is. So to find all those things out, I need to know what the potential is as a function of tau. So I have to go back to what V of tau is. And I'm just going to turn the crank using this supergravity formalism. And what happens is, the first term here, you get a series in 1 over tau. It starts off at 1 over tau squared because that's the thing that's scale invariant, it turns out. That's the thing that scales the same way as the rest of the Lagrangian does, but there's corrections. And so the A term and the B term are things that break scale invariance, and then they're smaller than the first term because they're down by powers of 1 over tau. The coefficients A, B, and W, X, it doesn't matter what they are, but they depend on the other fields, and they can depend on logarithms of tau because if you think about it, loops generate logarithms of mass ratios, and the masses are all proportional to 1 over tau, so you can get logarithms of tau through mass ratios. And so that logarithmic dependence on tau will be important. So I want you to keep in mind. The important thing, though, to start with is that the coefficient of 1 over tau squared, first of all, that 1 over tau squared term is not small. You know, the 1 over tau squared is scaling with tau the way that 4 powers of a standard model mass would. That's exactly how big the naive vacuum energy would have been. And so there's nothing particularly small coming from the scale invariance in this potential. But because it's supersymmetric, the coefficient of the 1 over tau squared is a square of something. And so it's positive. That's the important thing. And then the corrections are whatever they are. But because that first thing is a positive thing, you can imagine if I have some other field, this is where I can make a relaxation mechanism. If I have some other field in my problem that Wx depends on, it's going to love to minimize that first term by making it 0. It won't be exactly 0 because the subdominant terms pull it away from 0, but it'll minimize at a place where Wx is order 1 over tau. So all of these terms are going to turn out to be 1 over tau to the 4th in size once we're done, if I have a field like that, which can relax to minimize that first term of the potential. That's the thing, that's the new ingredient that will be the thing that will make the vacuum energy smaller than it would have otherwise have been. And once we're done, we're going to be left with a potential that goes like 1 over tau to the fourth times a function of the logarithm of tau. And the nice thing about logarithms is that I can have, if that function was a quadratic polynomial in log tau, I can stick in coefficients that are no bigger than 60, and I can give you minima, which are 10 to the 18, because the log of tau will turn out to be 65. So if I take, what I'm showing you is a plot of the potential if I take u to be a quadratic function of log tau, and you can kind of see that it's not difficult to get a de Sitter space, it's not difficult to get anti-de Sitter space, because you're perturbing away from flat space, essentially. And there's a story about keeping control of the tau, 1 over tau expansion, which I won't go into, but if someone asks, I can say more about. Now, there's an interesting thing about the numerology here, is if the potential at the minimum is 1 over tau to the fourth, as a function, the standard model masses are going like 1 over the square root of tau. That means that the potential looks like it's going like the standard model mass to the 8th power divided by the Planck mass to the 4th power. That's actually numerologically a good expression. It's a famous statement that the weak scale squared over the Planck scale is the scale of the cosmological constant that's been measured. And this is capturing that scaling automatically. It's not quite fair to say that it's capturing it numerically, because the dangerous thing in these theories are the supersymmetry breaking partners of the standard model. What I should really be doing is using as a benchmark, how big is the vacuum energy that they would have given me? And that would have been F star F, if F was my supersymmetry breaking scale. And it turns out with this potential, the prediction the potential gives you is what's shown here. It's suppressed by 1 over tau. And that suppression is coming about because of this combination of supersymmetry and scale invariance, suppressing the correction to the potential by 1 term in the expansion more than you would have thought. So that's the way that we get 1 over tau once more than we expected to. And it's because of that basic underlying mechanism. And so if I just take the numbers off the shelf that I would have gotten from this by minimizing that potential, I get 10 to the minus 90 Planck units. And we wanted to get 10 to the minus 120. So this is not successful, but I haven't tried to tweak anything yet. It just shows you that this is doing better than any other model has. And I want to focus on what's wrong with the model before I close. And what's wrong with the model is that these scalars are very light and they couple in a way which should be seen by tests for gravity. So the bottom line of this line of reasoning is I want to trade the cosmological constant problem for a model building problem of seeing if this kind of a theory can evade tests of gravity. So let me bring you to what the tests would be. So I'm just reiterating that the cosmological constant problem is we're making progress on it. But the important thing is that this dilaton tau, if you ask what its mass is from that potential, it's very light. It's basically the Hubble scale. If that potential is dominating in the energy, as it would be doing now, if it's the dark energy, then the mass for the dilaton would be super light, and so it should be seen in tests of gravity. Whoops! All right, time's up. Okay, my conclusion slide is the next slide, pretty much. So I'm just about done. Bottom line here is that a robust consequence of this whole line of reasoning, because the scale invariance played such a central part, is 2 things. The scalar field is light, and it's technically naturally light. We're normally taught that light scalars, you have to fine tune them to be light. But actually what's happening here is that if you have a natural understanding of why the potential is small, that will automatically make gravitationally coupled scalars also light. And this is an example of that, it turns out. And that's dangerous because they're coupling to the standard model in a predictable way. We're coupling through a scaling of the metric. And so they're coupling like a Brans-Dicke scalar does. And the size of the coupling is predicted to be 1 over root 6, which is way too big. The bounds on those couplings is 10 to the minus 5. So the problem with these models is, can you evade the contributions of scalar fields like this in tests of gravity? And it turns out that it's not obvious that you can't, in the sense that the response of the model building in this line of thinking is now asking, are there screening mechanisms that allow macroscopic sources of gravity to couple more weakly to these fields than they generically would have done, along the lines of the chameleon screening mechanism that has been proposed 20 years ago, probably. But unlike the chameleon mechanism, you need a mechanism here that can come from string compactification. And I can say more about the best case scenario for that if someone asks. So that's the ongoing research is how do the tests of gravity work in these models? It turns out that, just as a drive-by, because the masses are all field dependent, they can be time dependent cosmology. That introduces a very attractive way of dealing with the Hubble tension. You don't have to do it, but it's there if you are looking for a solution to the Hubble tension. And if you're interested in what this would mean for colliders, it's very, very similar to what happens in supersymmetric large extra dimensions. Large extra dimensions, people focus on the emission of, say, gravitons into the extra dimensions, so missing energy signals. Supersymmetric versions of that, there's other fields in the extra dimensions as well. And so there's other channels in which you can find, again, missing energy signals. And it's not an accident that this is what colliders would see, because the symmetries I'm talking about are the kinds of symmetries that can emerge in those kind of extra dimensional constructions. And it's kind of interesting that this is being rediscovered by the landscape people, that they're now finding that extra dimensions, large extra dimensions, and in particular supersymmetric ones, are the ones that they're interested in. But I think you don't need to give up the robustness of the symmetries to make that connection. So let me conclude. I'm arguing that UV properties can be predictive, but I'm arguing that you should look at the robust symmetry properties in the gravity case before you start looking at bespoke claims of UV sensitivity that are conjectural, because the symmetry properties are the ones that there's no doubt that they will be constraining how the low energy limit of your theory behaves. And so if they're already doing something good for you, exploit those first, because I think those are the informative things. There's very rich physics at low energies. And in particular, if you're successful in driving the scalar potential down, as I think the scale invariance would like to do, then it brings in a lot of light degrees of freedom that we're not used to in particle physics thinking about, because the naturalness issues for scalars change when the potential becomes small, it turns out. And the last thing is the open question. The reason I don't think these models are a success yet is, at face value, the simplest models that I've presented so far, although they give you a much suppressed vacuum energy, they also give you a Brans-Dicke scalar that's very light that you would have seen in solar system tests, for example. And so the model building issues here are, how do you hide those light gravitationally coupled scalars? But I'm thinking that's a step forward. You know, we've been decades trying to solve the cosmologic constant problem. If you can trade that for a model building problem for scalars in the solar system, that's a good trade, I think. And we should explore that direction before we give up. So thank you for your time. Sorry for running late.
Okay, thanks a lot, Professor. So I guess there are questions. So please, if you have a question, just, okay,
Yeah.
it's okay.
Yeah. So if I understand correctly, but first of all, thank you very much for your talk. Yeah.
Oh, thanks for coming.
Yeah, I really learned a lot of new things. Yeah, thank you. Yeah, but my question is about low energy impact of gravity, or in your framework, in the framework of your approach or your model. So then, what is the low energy phenomenology? Basically, or signal. Basically, this is missing energy.
Yes.
Due to this, yeah, but okay. And can you give an example of dilaton interaction due to dilaton? I mean, this missing energy events due to production of dilaton production, right?
So I should clarify that, because the missing energy is not coming because of dilaton emission, because the dilaton is coupling like the graviton does, and so it's coupling in a way
tau.
which is way
yeah. This is a tau, due to tau.
Right.
This
so tau is way too weakly coupled to be seen in colliders. But what happens is that if you kind of look at what the UV completion is for this theory, something has to happen at an electron volt. It turns out that the theory that I showed you, one way to see that is that if you at face value, if you took the theory that I showed you, where's the Lagrangian here? Here, that axion, the decay constant for that axion is m Planck divided by tau, and the way I told the story, m Planck divided by tau, that's essentially the neutrino mass. So that's like an electron volt scale. And so that's telling you that the decay constant for this axion is extremely small. And so there should have been a problem with the axion physics at an electron volt.
Yeah.
And it's true that there has to be a UV completion for this kind of a theory at about an electron volt. But the thing is, it's known what that completion is. That completion is an extra dimensional model, essentially, where it's a large extra dimensional model where to have the extra dimensions would have to be at an electron volt size. And so you can only have two of them that large. But in that kind of a model, what typically happens is that the bulk in those kind of models is supersymmetric, and that's kind of why the gravity sector is very supersymmetric. But then the branes on that model are not supersymmetric because they break supersymmetry. And so there is a UV completion that goes beyond this at the electron volt scale, and that one would be essentially large supersymmetric extra dimensions. And so the thing that you see, if that's the way the world works, then what you would see in colliders is not the dilaton. It's all the stuff in the extra dimensions is what you're seeing in the same way that you would have done in large
light tower of
there's towers of everybody.
Yeah, well, but it should be sufficiently light towers.
Towers were spaced by electron volts, so it's very much like a large
electron volts. But the absolute scale of this tower should also be quite small, or not? To be
when you say absolute scale, what do you mean there? You mean the spacing between the levels?
But you said that the spacing in this tower is of electron volt like that.
Yes.
Spacing.
Right, but then
what is the overall scale?
It becomes the gravity scale in the extra dimensions, which in those models is the weak scale. Essentially, it's a 10 TeV kind of scale. And so that you match onto the phenomenology of the large extra dimensional models with the supersymmetric, with extra fields in the extra dimensions, in the way that, and that was a kind of thing that was explored in the 20 years ago. And the bounds on those models are that the gravity scale in the extra dimensions has to be at least 10 TeV. And we knew that before the LHC turned on, coming from things like energy loss from red giants and that kind of thing. But that's the only bounds. And so there could be signals for missing energy from that kind of emission, and it's happening. It's detectable because of the usual large extra dimensions argument that each Kaluza-Klein mode is gravitationally coupled, but the phase space of all the modes converts that into a TeV kind of an interaction scale.
Yeah. Okay, I see. So this is the feature which can be used to distinguish this signal, right, from other missing energy signals.
In principle, yes, although it's a hard business because missing energy is missing energy, right?
Yeah, right.
Yeah, so if you see missing energy, then you can start asking kind of where did it come from. But it's the first approximation, everybody has the graviton. So that means that in the pure large extra dimensions where all you had was the graviton, you always have that signal. But then you have these extra channels of these extra other fields. Probably the most, if you did start seeing missing energy, probably at that point, the more useful discriminant is neutrino physics, because in neutrino physics, normally you're told you could have sterile light fields, but in these extra dimensional models, you're being told why they're light. And you've got all these fermionic towers in the bulk, and they're light because they're tied to gravity by supersymmetry. And there's lots of ways in which neutrinos can start mixing with those light degrees of freedom. And it's probably true that if you're looking for bounds, you might see them first in neutrino physics. Once you can always make them small by making the gravity scale high, but if you were to see missing energy at the LHC, now you've nailed down what the gravity scale is, then the size of other effects would be fixed. And then I think that's the variety of things you could look at there that discriminate models.
Okay, yeah. Thank you.
Yes, so does anyone has more questions? I don't see much. Are you sure? Please. This is your opportunity. Yes, I have a very naive question, but I would guess there are better questions than mine.
They're all good.
Yeah, I wonder actually, is there a preference theoretically from beyond standard model theories with UV completion and theories without UV completion? So is there a preference?
I would have said no. So I'm kind of old school. I would have said that I don't, if I could solve a real problem at low energies and then someone tells me that I can't UV complete it to gravity, I would say, well, too bad for gravity. Because someone will figure out how to complete it for me. Is the way that's the attitude I would normally take. But I would say that's just me. I think that there's now a significant chunk of at least the string community, who take seriously the swampland program, where they think that it's actually a useful criterion to ask whether or not your theory can be completed. And they think that it's possible to do that. So they think that they have testable criteria you can use to decide if you're in the swampland or not. And I'm glad that smart people are worrying about that, but I personally don't think that that's. I wouldn't want to tie my hands that way until I had to.
Thank you. So, more questions? Well, if not, I would like to thank you again, Cliff, for this nice talk.
Thank you again for the invitation.
Yeah, and I guess we see everybody in the next webinar. So, bye-bye.
Take care.
Bye.
Thanks
Thank you.
again. Bye.
Bye.